Good morning, good afternoon, good evening, everyone. I'm happy to talk about semantic segmentation, object detection, and high-resolution backbone with transformers. Let me first introduce the background of transformer. The transformer block consists of two basic components. One is attention, the other is FFN. The FFN module actually is also called one-by-one convolution or point-wise convolution, or also named as point-wise MLP. The attention unit actually is different from convolution. Let me talk a little about the attention. Basically, the attention can be viewed as searching for relevant keys and connect their values. Here, let me introduce the process. First, we compute the similarity between the query and each key, and then normalize the similarities. In the second step, we update the embedding for the query by computing the averaged by computing the weighted sum, and the weight actually is computed from the similarity. So now let me first introduce the work about using transformer for segmentation. Actually, this work was published by last year ECCV. So what is segmentation? Actually, here example, let's look at this region, and this corresponds to the segmentation result. Actually, we want to label each pixel using the category of the object that the pixel lies on. For example, for this region, we label all the pixels as a car. So as we know, the convolution network, for example, ResNet or HRNet, can be directly used for segmentation. But actually, to learn strong representation for each pixel, various contextual models have been developed. Here, I will talk about the typical context method. Here, it is called multi-scale spatial context. The representative examples include, for example, PSPNet and DETR. The two methods actually aim to expand the scope of each convolution. For example, in PPM, it uses pyramid. In contrast, in SSPP, it uses dilated convolution to expand the scope. But these two methods actually only explore the spatial context without considering the content information. So our work we called object contextual representations. This actually based on the so-called object context. So we start from the definition of segmentation. The label of one pixel is a category of the object that the pixel belongs to. For example, this red pixel is labeled as a car. This is because this pixel lines the object car. So motivated by this definition, we want to augment the pixel representation by mine the object context and then using the object context representations. So this pipeline actually was initially appeared in our ECCV paper, but in this talk, I will use transformer language reformulate this pipeline. Here, this is a new pipeline. Actually, this is equivalent to the previous one. There are two basic modules. Two basic modules, closed tension and another closed tension. Let me explain more about the two closed tension modules. For the first closed tension, we aim to learn image-dependent category embeddings called object contextual representations. Here we introduce K category embeddings served as the queries for this closed tension module. And the pixel embeddings are used keys and values for this closed tension module. So here I want to explain that the K category queries actually are model parameters, and they are the same for all the images, not specific for one image. But use this closed tension, we want to learn the image specific embeddings. So in this closed tension, for each category query, we want to give higher weights for the pixels that belong to the corresponding category. Then we aggregate those pixel embeddings according to their attention weights and add them to the K category queries. To help this, we also introduce a loss for this closed tension module by using the ground truth segmentation to supervise the attention weight maps. For the second closed tension module, we want to augment the pixel embeddings by using the output of the first closed tension, the object contextual representations. Again, we want to aggregate some category embeddings, or all the we want to aggregate the category embeddings according to their similarity between the pixel queries and the K categories. Notice that in this closed tension, the query is pixel embeddings, and the keys and the values are the K image dependent category embeddings. After that, we have augmented pixel embeddings. Then we can classify each pixel to get the labels for all the pixels. So actually, that's all for our method. So now let me introduce some results. Here we compare our method OCR with SPP used in DeepLab v3 and PPM used in PSP.NET. We compare the three methods in terms of parameters, memory, cost, and theoretic complexity, and runtime cost, and the segmentation quality. We can see that our method actually better than SPP and PPM in terms of all the 5 metrics. Now let me introduce more results. Here, we report the results on Cityscapes test. We can see that OCR with ResNet 101 already get the best results compared with previous results when we submitted our paper to ECCV. Combine HRNet, the result is even better. And we also have results for other 4 datasets, particle context. We can see that in terms of 2 evaluation metrics, one is for 59 classes, another one is for 60 classes. The 2 results actually better than the previous results. For leap value, for leap, the leap density is about the human passing. Again, we can see that our results are better than previous method. We want to emphasize that in our method, we do not use extra information, for example, post information or agent information. If we also consider those information, I think our results will be better. It's ADE 20K validation. Again, at that time, our method actually get better result, but I will show combine the strong backbone, our result would be better. Same observation for Cocoa staff. So actually, recently we also try to combine self-retention into our method. For example, we add self-retention in this module to explore the relationship between the care categories. We also add a local attention module to augment the pixel retention. Actually, we found that by adding the two modules, we can get around 0.5 MROU improvement. Actually, we also see some recent method. Actually, for example, HRFormer and MaskFormer both explored attention mechanism for semantic segmentation. So here's a summary for this part. We reformulate OCRNet using the transformer language. And in this new formulation, there are two close attention modules. The first close attention actually aims to learn image-dependent category limitations. For the second close attention unit, we want to use the image-dependent category limitations to augment the pixel limitations. Now let me introduce the second work, Conditional DETR for fast training convergence. This work was published in this year's ICCV. So here first, let's look at the problem of object detection. By object detection, we mean to localize the object as well as predict the object category. So our method will improve the DETR approach. The DETR approach actually published in last ECCV. This DETR approach actually applies transformer encoder and decoder with Hungarian match method for an end-to-end object detection approach. Note that in the DETR approach, we do not need the post-process NMS. So the decoder module actually is one of the critical components in the DETR approach. Here we want to talk more about the DETR part, the decoder part. There are two components in the decoder part. One close tension, one self tension. So how DETR decoder works? Actually, for close tension, it aims to search for the four extremities of the object and the region inside the object for classification. Here we only focus on the four extremities. So after finding the four extremities, the cluster module will aggregate the corresponding embeddings. For the late class prediction and the box prediction, as well as query refinement. For here, I want to illustrate the four extremities. For example, in this example, we can see that the top, left, right, and the bottom extremities are found by the closed attention module. Similar observations can be found in for zebras and other elephants. For the other module, self-tension, actually the self-tensions aim to collect other decoding embeddings. Here, each decoding embedding will correspond to one prediction. And actually, it is a key component for duplicate removal. Because of this module, we can replace NMS and do not use NMS. Though the DETR approach is very promising, there one major drawback. The training convergence process is very slow. In the original DETR approach, it actually needs 500 epochs to get a reasonable result. But if we only have 50 epochs, we can see that the score is very low. So our study shows that the slow convergence actually comes from the decode close attention module. Here we can see that in this figure we can see that actually this figure shows the spatial attention weight maps for the close attention module. Here we can see that for 500 epochs, the full boundary of the box, for example, top, bottom, left, right, actually are accurate. But for 50 epochs, you can see that for the left one and the right one, the two actually are not correct. The reason is that though the query for the clustering module, here actually the query is the decoding embeddings and the object query. Though the decoding embedding contains both box information, we call it spatial information, and content information, but the box information and the content information is mixed together and entangled together. This means that it is hard to solve as two rules match content and box information. This is the reason. Another observation is that the object queries and the key position embeddings actually do not contribute a lot. If we remove object queries and the key positional embeddings from the second decoder layer, we only observe 1.5 AP job. Actually, this implies that object queries and the key position embeddings in current design actually are not so important. So before seeing our approach, let me re-illustrate the closed attention part. For the closed attention part, we have object queries as the spatial queries and the content queries. In addition, for the values, it's just encoder output. And for the keys, it contains content part and spatial part. In the original DETR approach, object queries and the content queries will be summed together. So what we do actually is very simple. we learn conditional space queries to replace the object queries. Here, we learn the spatial queries from the decoding embeddings and the so-called reference point. I will talk about what reference points are. The key difference from the initial approach is that we use decoding embeddings to help form the spatial queries. So for computing the spatial query, actually it is very simple. Here, the inputs include reference points and the decoding embeddings. Through some simple operations, then we can get the so-called conditional spatial queries. Here, what are reference points? Because our purpose is that map the box information content in the decoding embeddings to high dimensional positional embedding space. In the 2D space, actually, the decoder embedding only contains the transformation of the box from some reference points. The reference points could be the coordinate origins or knowable 2D coordinates at model parameters. Actually, in our experiments, we found that when we learn a reference points or using object queries to predict the reference points are better than the 2D coordinate origins 0, 0. Actually, we also observed that if we do not use the reference points, only use decoding embeddings to formulate the spatial queries, actually the result are bad. Here, let me show after using this conditional spatial queries, what have we changed for the spatial attention map? We can see that this corresponds to our approach with only 50 epochs, compared with the initial DETR approach with 50 epochs. We can see that the left and the right extremities are correctly highlighted. So in terms of training process, we can see that the red curves correspond to our approach with different epochs. We can see that within 50 epochs, our result already slightly better than the initial DETR approach with 500 epochs. Actually, in this experiment, we will use the backbone resonate with dilated convolution. So let's look at how conditional DETR work. Again, here we show three kinds of attention maps. The first row corresponds to spatial map. The second one is content map. The third one is combined map, actually used for aggregate the extremities embeddings. For the first column, actually corresponds to the 4 extremities, but for the last column, actually it corresponds to the region highlighted for classification, the object classification. Actually, in our approach, we have the same attention heads, 8 attention heads. Here we only show 5 heads. Actually, for other 3 heads, 2 of them correspond to 2 extremities. Another one actually still corresponds to the region inside the object for classification. So if we look at the second row, we can see that the extremities are not correctly highlighted. For example, in this case, the 2 regions are also highlighted. For the second one, actually, it corresponds to the top extremities, but we can see that this top one and this top one are both highlighted. But if we combine them together, we can see that this corresponds to the left top right bottom and a region inside the object, we can see that the tangent maps are very good. Same observation for another example. Here let me reduce the result. For this part corresponds to the comparison with DETR. We can see that with 75 epochs, our result is the same as the DETR approach with 500 epochs. With more epochs, our approach gets better result. For the dilated version, resonate 50, we can see that for 50 epochs, our result is slightly better than the DETR approach with 500 epochs. Compared with other DETR variants, our result is also better. So this table shows the result for Resonate 101. Again, we have similar observations. With 50 epochs, our result is very similar. The DETR approach with 500 epochs, but with 75 epochs, our results is better than DETR approach with 500 epochs. So actually, we also found that there are two concurrent works. Maybe there's some other method concurrent to our works, but here we just mentioned two works. One is so-called spatially modulated co-attention, the other one resilient transformer. Here, for the left one, spatially modulated co-attention actually is very close to our approach. They also try to modify the cross-staging part by modulating the cross-stage weight maps. But compared to the realization, actually our approach is more interpretable. Actually, our approach just highlighted the four extremities, but for SMCA, the highlighted regions seems not so interpretable. Now let me conclude this part. So we propose a conditional DETR approach. It's very simple, just modify the spatial queries for the cross-tangent part. And we learn spatial queries so that the dependence to the strong content queries is weakened. And actually, our ongoing work is try to connect the object queries with the well-known anchor. We want to enrich object queries from position to box. Now let me use the third work, HRFormer high-resolution transformer for dense prediction. Actually, this is an extension of our previous work HRNet by using transformer. Actually, this work was accepted by NeurIPS this year. So let me talk about high-resolution network. As we know that HRNet can learn high-resolution representations with stronger position sensitivity. The key is to maintain high-resolution representations through whole network other than recovering from low resolution like UNet. So actually for architecture design, HRNet is designed from scratch instead of based on previous classification networks. So this is the architecture for HRNet. So HRNet initially designed for pose estimation, and later we extended it for segmentation and detection. Actually, it is a universal architecture. And the application actually are beyond pose estimation, segmentation, alignment, object detection. Can be used other dense prediction problem or position sensitive problem, for example, optical flow, and for example, image synthesis or image translation. So another work transformer, vision transformer, as we know that this actually is iClear work. In this actually just apply the transformer pipeline directly to image classification. It partitions the image into multiple patches, and each patch is viewed as a token, then perform the attention over all the patches or over all the tokens to gradually refine the representations. So for the VIT, it used global attention. By using global attention, actually one drawback is the complexity is very high. The complexity is quadratic with respect to the number of tokens. So we instead use a local window attention. Actually, it is very simple. For example, we just partition the image into non-overlapping windows and then conduct self-attention in each window separately. Here is we use this kind of figure illustrated. We illustrate this partition transformer block. But because those windows are non-overlapping, this means that there is no information exchange across those windows. To solve this problem, in the FFM module, we introduce a 3x3 depth size convolution. For this depth size convolution, actually its complexity is very low. The parameter complexity is also very low. By introducing this 3x3 depth size convolution, we can connect the nearby windows. For example, in this case, for this operation, for the convolution at this position, we can connect this window and this window. And for this window, even it can connect the 4 windows together. Actually, this approach is very simple. So by architecture design, we simply modify HRNet architecture. We keep to use the convolution for the first stage. And for the second, third, and fourth stages, we do not change we still use the convolution for the close resolution fusion and only replace the convolutions in the same resolution using the previous described partitioning transformer block. Actually, this change is very simple. In particular, I would mention that here we use depth-wise convolution instead of the normal convolution because actually for attention it is something like depth-wise convolution. For depth-wise convolution, we can save computing cost and save parameter cost. The architecture is very simple. Here by though we simply replace some convolutions use the attention modules, but actually because for example in this stage we contain several resolutions from high, medium, and lower resolution. In each resolution we use the same size, same attention size, same window size. This means that we actually can capture short attentions and long attentions. In other words, this module is a mixture of short and long range attentions. So let me introduce the result. First, human pose estimation. Here we describe many results. Here let me focus on HRFormer B. B is base. B means base. We also compare it with HRNet W48. The two methods with similar epochs, similar flops, and similar, and not similar actually for HRFormer. The parameter complexity and computation complexity is lower than HRNet W48. But we can see that the AP score is higher. Compared with the improved version, by solving some problems in ground truth heat maps generation process and other process, we can see that our method is also similar with the UDP and the DAC. And here are results for test dev. Again, our method actually is better than previous one, but compared with the token pose, it also actually based on transform method. Our method is slightly better, and the G flops are also slightly large, but for parameter complexity it's larger. We want to see what we can borrow from the token pose method to further improve HRFormer. Here let me see another dense prediction problem, semantic segmentation. So here we compared with several representation methods, transformer backbone and a convolutional backbone, and our method actually is a mixture of convolution and transformer. Actually, we do not directly use HRFormer for segmentation. We combine with OCR, mentioned in the first part, object context representation method. We can see that for Cityscapes, our method is the best one. For Coco Staff, our method is also based. But for ADE, we can see that for ADE, let's compare with HRNet with HRFormer. The score is improved a lot, and our score is very similar to other transformer-based approach. For example, compared with Swin B, our result even better. And for partial context, our method lower than DPT hybrid, but the result from DPT for ADE actually is lower than ours. So let's see some operational studies. The first one, what's the effect of 3x3 depth convolution? We can see that if we include the 3x3 depth convolution, we can see that for the partial context segmentation and Coco pose estimation, the score actually improved a lot compared with ImageNet. And here is more comparison with HRNet on ImageNet, partial context segmentation, and Coco pose estimation. Again, in this case, we can see that the improvements on ImageNet classification and segmentation actually is more significant than Coco pose estimation. In addition, if we look at the parameter complexity and the computing complexity, we can see that actually our new method HRFormer is lower than HRNet. So compared with other non-high resolution method, for example, VIT, DIT, Swin, on Coco pose estimation, we can see that our approach is better than the previous one. Even for this method, Swin and the VIT, they used 20K ImageNet for pre-training. This shows that for dense prediction, high resolution is still necessary even we have already used transformer. Again, in our method, we use 3x3 depth convolution for connecting non-overlapping windows. And in the recent pre-swing transformer, they use shifted windows. Here we compared 3x3 depth convolution with this shifting window method. We can see that let's focus on this row and this row. We can see that without shift window and with shift window, we can see that for image classification, with shifted window, the result even lower. And a similar observation for particle coordinate segmentation and Cocoa pose estimation. This means that 3x3 depth convolution is enough, but we still don't know why. In this case, using shifted windows, the results become poor. So here, let me introduce some other concurrent works with local attention. For example, twins, shuffle transformer, actually they are about local attention and global sparse attention. And the Swin transformer uses horizontal attention and vertical attention. Actually, we want to show that for local attention, global attention, in 2 years ago, we proposed so-called interlaced sparse self-attention. Actually, at that time we only used for segmentation, but actually they are the same. And actually, this method based on our previous method, interleaved global convolution. For horizontal and vertical attention, actually 2 years ago, the method is called CCNet. Actually, they already studied for segmentation. Actually, in terms of matrix decomposition, actually, those methods can be explained in the chronic product form. In this case, here X corresponds to the pixels. We can reshape the vector form of the pixels into matrix form. Actually, for twins and C-swing, actually they reshape the vector form into matrix form in different methods. Here's a summary for HRFormer. Actually, we combine HRNet with transformer together to learn high-resolution representations. There are two properties in HRFormer. One is actually this structure actually is a mixture of convolution and attention. The other one, we mixture short or long and long attention together. So here we want to discuss something about the transformer for computer vision. So we think transformer for downstream tasks for segment detection might be more promising, and we need more exploration. For transformer for upstream tasks, for example, image classification, we still need more study to see whether this kind of attention is better than dynamic depth size convolution. Actually, we have work in the archive try to study the relation between local attention and dynamic depth size convolution. We also have a figure to show the relation between convolution networks and attention-based transformer networks. So here, actually, we released the codes for OCRNet, Conditional DETR, and HRFormer. Also, we released dynamic depth size convolution and have comparison with local VIT. Thanks for attention. Thank you.